Hello, and welcome back to CS631 Advanced Programming in the Unix Environment. In this last segment for week 6, we will look at process control, how new processes are started from an executable, and what happens when they terminate. This is a prerequisite for the materials we'll cover in the coming videos, where we discuss process relationships in much more detail. Also, there will be zombies, so, limber up. But let us go back to our first lecture, where we wrote the world's simplest shell. That program looked like this. For every input line we receive, we fork a new process, exec the given program, and then wait for it to terminate. So let's take a closer look at what each of these three calls does, starting with fork. The fork system call is a bit peculiar, because it returns twice. That is, it creates a new process resulting in two copies of the current process, meaning it will then return twice, once in the original process and once in the newly created process. We call these two processes the parent and the child process respectively. The new process is nearly identical to the parent process, with the following differences. The child process has a unique ID. This should be reasonably obvious, as we established in our last video that a process ID identifies a single process uniquely and thus cannot be shared. Likewise, and equally logical, the child process has its parent process ID, the PID of the process that called fork. Makes sense. The child process gets a copy of the file descriptors open in the parent, pointing to the same data structures. This is interesting, as it means that, for example, a read in the child will change the offset on the same file descriptor in the parent. We'll illustrate this in a second. The child's resource utilizations are set to 0. That seems only fair too. The process was just born, so having for example a limit on the CPU time get applied would seem confusing at best. Finally, it's important to note that while we talk about the child and the parent process, it may seem intuitive to assume a specific order of execution after fork returned. There is none. You may observe the child to always appear to run first after fork, but that is an implementation-defined behavior that you cannot rely on. The order of execution after fork returns is unspecified. To illustrate in a bit more detail the differences between the parent and the child processes, let us revisit the visualization of the data structures relating to open files. Here, this process has 3 files open, each with their own file table entries. When the process calls fork, we get a second copy of this process, inheriting the file descriptors of the parent. Note that the child process's file pointers do point to the same file table entries as the parent process's pointers. That means that an operation on either of these file descriptors in one process affects the other. Let's show this in action. Here we have a small program that opens a file, prints its PID, reads some data, and then forks. After it forked, both processes now have an open file descriptor with the current offset at the end of the data chunk it read, 32 in this case. The child process then L-seeks 32 bytes forward and goes to sleep to let the parent read. It then reads data itself. The parent goes to sleep immediately to give the child a chance to seek. And then the parent reads data. In the read data function, we determine the current offset, print it, and then read some data. Here we go. Now, when we run this program, let's see what happens. The process ID is 361. The program then calls the readData function and reports its current offset 0, which makes sense since we just opened the file and thus find ourselves at the beginning. This function then reads 32 bytes, so at the end of the function call and before we fork, our current offset is thus 32. After we fork, the child process with PID 999 then seeks forward 32 bytes, leaving the offset at 64. The child then goes to sleep, and the parent calls read data again, where it reports a current offset of 64, showing that the child's LC changed the parent's offset. The parent completes its read, advancing the offset by another 32 bytes, which is then reflected when the child process calls read data and finds itself at offset 96. Okay, so file descriptors are duplicated and the offsets are shared. But let's look at another example. Here we have a program with a few variables, which makes a call to write, then calls printf before it forks. Parent and child both operate on the global and local variables in different ways, then both will print out the current pid, ppid, and the values of these variables. There shouldn't be any surprises here, so let's run it. Okay, so the current shell has a process ID of 848, with the parent process, process ID 1726, reports as its ppid. The child process ID 2154 reports 1726 as its parent. Each incremented or decremented the global and local variables, showing that they each got a copy of these variables, not references to the same variable. Okay, but now let's try this. We run the program again, and this time we pipe the output into cat. That really shouldn't change anything, should it? But hey, what's that? Why do we suddenly get a second before fork statement? Our code clearly included only a single printf call before we forked, so how come we now seem to have gotten the child process to also print out this message, even though that printf took place before the child process even existed? To explain this, let's look at how the two flows differ. We start out with a process that has its variables declared. It then calls write. Write is unbuffered I.O. and immediately writes the data to standard out file no, which is connected to the terminal. Next, we call printf. Printf is buffered I.O., so it doesn't write directly to the terminal, but instead writes to a buffer. If standard out is connected to the terminal, then our output is line buffered, meaning when we encounter a carriage return, we flush the buffer and the message is printed to the terminal. And then the buffer is drained. Next, we call fork. And so we get a copy of the current process, nearly identical to the first, with only the pid and ppid being different here. After that, both child and parent perform their respective operations on the variables before they each call printf. This call to printf again writes to the buffer, which then, upon encountering the carriage return, are flushed to the terminal. Okay, so far so good. Perhaps you already have an idea what happened when we redirected output into a pipe, but let's take a look here. Again, we start out with our process before. We call write as before, and again write being unbuffered immediately writes to standard out file no, which is now connected to a pipe. We then call printf, which, again as before, fills the output buffer. But since standard out is now connected to a pipe, it no longer is line buffered. That is, we keep the data in the buffer without flushing the buffer, and then call fork. Fork does its thing and creates a copy of the current process, including the output buffer. That is, now our child process has an unflushed output buffer that contains data. Both processes continue with their operations, and then call printf to write their information to the output buffer, appending to whatever data is already there. Upon program termination, the buffer of each process is flushed and written to the pipe, which then dutifully writes it to cat, which copies it to its standard out, our terminal. In this way, we've seen how fork can lead to a child process retaining data from the parent, and this explains why in such cases it may be preferable to explicitly flush any buffers before calling fork, just like it might be useful for a child process to call _exit instead of regular exit, to avoid flushing of any buffers it may have inherited from its parent. Ok, using fork we can create a new process, but the parent and child are identical, and any differences must have been coded into the if pit equals 0 else logic. More often, though, we want to execute a different program altogether after we've forked. To do that, we use the exec family of functions. As you can see here, there are several variations, each differing only in the way it accepts the arguments. Each of these functions is merely a front-end for the execve system call, and from our discussion of the process startup in previous videos, we already know that we will provide the argv and the environment to the new process. Note that the exec functions do not return. They replace the current process with a new image from the executable specified. If exec ever returns, then you encountered an error. The various exec functions differ in the arguments they accept, and you can easily remember which function uses what type of argument by looking at the name. If it has a v in its name, argvs are a vector. If it has an l in its name, argvs are a list. If it has an e in its name, it takes a char*const envp array of environment variables. If it has a p in its name, it uses the path environment variable to search for the file. For all other functions, you have to specify a complete path to the executable. Note also that you can control the entire argv vector or list, including argv0. That is, you can invoke a command foo and pass an argv0 of bar to exec, and the process table will then show the command as bar. Give it a try to confirm. When you call exec, there are a few side effects that are worth noting. Open file descriptors are inherited, unless the close and exec file flag was set via fcontrol or at file open time. Ignored signals in the calling process are ignored after exec, but called signals are reset to default. We'll discuss signals in more detail in a future lecture. Our process inherits the real UID and group ID. The effective UID and group ID is also inherited, unless the executable was set UID, set group ID, as we've seen in previous lectures. After we create a new process, and possibly execute a different program, we have to have some sort of process control, as both child and parent are now executing simultaneously. To wait until a specific process has terminated, you then call wait. Wait suspends the execution of the current process until status information is available for any child process. If you want to wait for a specific process or a process group, you can use waitPit or the waitFor function. What does waiting for a process mean? On the one hand, yes, it literally means waiting until the process is terminated. On the other, and more specifically, it means we are inspecting certain information about a process that is no longer alive. Remember that our programs have a return code. Somewhere something has to do something with this return code. You may also be interested in the resource usage of a terminated process, how much CPU time is used, how much memory, etc., which the wait3 and waitFor functions can retrieve for you. So once we get back the status information about a process, we can then use a number of defined macros. wifExited and wExitStatus can tell you whether the process terminated normally and what the exit status was. We can learn whether a process terminated as a result of a signal, and if so, which signal, as well as whether it left a core dump or not. But a process may also be suspended, not terminated, and we can find out about that using wifStopped. Finally, wait will block until any process changes status, but you can also use waitPit or waitFor to check on the status of a given pit in a non-blocking manner. Ok, but why should you bother to wait for your child processes? When a process dies, the exit status information must remain available for inspection, so if nothing ever clears up this exit status information, then we have a process that's dead, but still running. In other words, we have zombies. That is what a zombie process is, a process that has died but that has not been waited for, meaning it continues to use up certain resources, such as the process ID and the resource utilization, exit status, etc. Here, let's look at an example. Here we have a program that intentionally creates a few zombies. We loop and fork, each time having the child process exit immediately, but without having the parent calling wait, thereby becoming a zombie. So, let's run the zombie maker. Okay, here we see that our program creates new zombies on each iteration, showing up in the process table with a Z in the status field. If we switch to another terminal and try to kill one of the zombie processes, we'll find that doesn't work. Duh, can't kill a zombie, they're already dead. Let's try to kill it harder. Still no luck. Okay, back to the initial window. The program finally terminates. Note that the program did not wait for any children, and that we had 5 zombies while we were running. But after the process terminates, we note that all the zombies are gone. This is because init will automatically wait for any orphan processes. An orphan process is a process that's still running but where the parent has terminated. When that happens, the kernel reparents the process to init, and when that process terminates, init gets a signal and then explicitly calls wait on that process to clear the exit status information. This process is known as reaping, because hey, sure, we're talking about zombies and other dead things. Knowing this, we now know how we can get rid of all the zombies. If we kill the parent process, all of the zombies will be reparented and init will reap them for us. Let's give it a try. Okay, zombies are being created. Let's switch over to the other screen. We still can't kill the zombies. But if we pick the parent process, then all the zombies disappear. Just like in any standard horror movie, where if you kill the first zombie, all the others die as well. Nice. Okay, enough about zombies. Time for a recap. We looked at how processes are created using fork. And we saw how fork creates an almost identical copy of the process, including file descriptors and buffers. We saw the different ways to call exec to replace the current process with a new process image. And we saw how to get back the status information and resource usage from a terminated process, and why we need to call wait to avoid zombies taking over our system, although init will helpfully reap any orphan processes for us. And with that, we'll terminate the current video series for week 6. In the next videos, we'll look more closely at process relationships before we move on to signal handling. Until next time, thanks for watching.